Time and frequency domain two-tone simulation based on periodic steady-state linearization. Modeling and simulation of electronic circuits play an important role in designing and fabricating electronics equipment, providing the circuit designer to accomplish their design specifications. Usually, in circuits containing independent sinusoidal sources, just the steady state is obtained for simulations, due to the absence of knowledge about the initial conditions and to avoid the additional complexity demanded by transient response. Steady-state analysis method can be divided as frequency and time domain methods. The frequency domain harmonic balance and the time domain shooting method have been developed for coupled device and circuit simulation, so a comparison of the performance of the two methods in this context is important. Large and small signal analysis are commonly applied in design of mixers and power amplifiers and in nonlinear noise analysis. The technique is based by seeking the linear response to a much smaller signal applied in circuits with a nonlinear element driven by a single large sinusoidal signal. At first, the nonlinear device is analyzed under large signal excitation only. Then, the device is linearized in order to create a time-varying linear small signal elements, and at last a small signal analysis is made. So, the main purpose of this work is to present a comparison between the methods in frequency domain using harmonic balance and in time domain using shorting method. The linearity value limits are also discussed with a single event transient analysis. The linearization technique can be applied for different electronic circuit analysis methods. As a general rule, it is necessary to differentiate the element equation in relation to its initial state for linearizing it. This equation describes the linearization of an unknown. In this work, x0 is the periodic steady-state response to a large signal one-ton excitation. The linearized circuit is then also stimulated by a small signal second tone. The frequency domain is known in literature as periodic alternating current (PAC). The application of PAC method, which uses harmonic balance method, linearizes the analyzed circuit around the steady-state response to a large signal one-ton excitation. When applying the harmonic balance method, the initial trajectory function to be used on linearization is composed of one constant corresponding to DC component plus their harmonic contributions that alternate depending on the numbers of configured harmonics, as exemplified in the first equation. This equation can be reorganized in order to become a multiplication of two vectors, one vector consisting of periodic time functions and the other one an amplitude vector composed of the DC component plus the configured harmonics contribution, as exemplified in the other equations. The voltage or current values to be obtained at the end of analysis are calculated by applying the superposition method. This method consists of adding the initial trajectory xhb with a linearized component xlim. To get xlim, it is necessary to differentiate the nonlinear component function around xhb. The obtained response can be reorganized in a multiplication of an amplitude matrix GHB and a column vector x1 tone, composed of the positive and negative fundamental component of the second tone and the harmonic contributions of the first tone. In this matrix, G0 until G8 are constants that indicate harmonic balance amplitude components of the unknown manipulated by the nonlinear element function. In time domain, at first, it is necessary to obtain the response of the fundamental frequency voltage source acting alone, and the small signal source is disregarded. The voltage and currents obtained are periodic signals for finite time steps, and the function period is 1 divided by f1. Furthermore, the nonlinear periodic function is calculated for this voltage source. The values found for the voltage are used for the next step, for calculating the circuit currents until we reach the final step. the final value of each state variable, which can be capacitor's voltage or inductor currents, is subtracted by the initially assigned value. In this equation, the unknowns with the subscription prev are referred to the values found at the last iteration. VB and VC indicate voltage over capacitors. After the end of simulation, the nonlinear function is linearized around the first shorting method result. Thus, it is now time-varying with frequency f1, whereas the voltage injected by the small signal source has frequency f2. The single event transient of the equivalent circuit is linear as well, and a new shorting method is processed. As the linearized parameter requires a trigonometric multiplication, the fundamental frequency of the linear is 1 divided by f1 minus f2. In this equation, VA-lin is the linearized voltage amplitude and Gn is a time-varying variable with frequency f1, result of derivative of the nonlinear trigonometric function. The schematic of the circuit used in this work is shown here. The values of C1 is 10 picofarad, C2 is 1 microfarad, R1 is 1 kiloohms, and RL is 50 ohms. The fundamental frequency f1 is 1 GHz and f2 is 1.1 GHz. The nonlinear element FNL, which in this paper is a voltage-controlled current source, and Vs is a two-tone sine wave voltage source with different amplitudes and frequencies. The different outputs or variations in the amplitude of excitation source Vs were observed using MATLAB software for simulating and plotting the waveforms of the shorting method and PEG simulation. In both approaches, two algebraic systems are needed to be solved. The first one is a nonlinear system and the second one is linear. In PEG, the number of unknowns in an equation is equal to 2 times h plus 1 in the nonlinear system and 2 times bigger in the linear system. H refers to the number of harmonics considered. In this study, it was used h equals 10. In shorting method, in the nonlinear system, the number of unknowns in an equation is equal to the number of state variables, which in this study are 2, and the linear system has 2 equations as well. Finally, it was processed a spice-like simulation, with the independent source injecting simultaneously both tones, and knowing this method always works, this will be used to access the linearization validity limit, make a comparison between both PEG and shorting method waveform results. This waveform was obtained by MATLAB by applying 0.2 volts to the second tone amplitude. This figure demonstrates that both methods present very similar results. Therefore, it is more useful to analyze which method requires less calculus and computer processing. Then, 1.2 volt was applied for the second tone amplitude. As can be seen in this figure, it is notable that the bigger the voltage amplitude applied to the second tone, worse the signal response behavior. It is also notable that the nonlinear function presents bigger values than scale current. Furthermore, there is a big difference between the spice-like simulation and the method's response. In both time and frequency domain approaches, the circuit is linearized around at one tone. It is used a large signal in the first tone, but it is only possible to use a small signal in the second tone. Upon the method calculus and computer effort being compared, the number of unknowns is higher for PEG. However, the complexity of shorting method is increased because it demands for one fundamental periodic transient analysis. As can be seen in simulation results, when the voltage amplitude in the second tone is increased, it is observed a greater amount of distortions and a big difference between the approach's results and the spice-like simulation. It follows that linearization is valid in the first case with small values of amplitude, but not for bigger values. This study was financed by National Council for Scientific and Technological Development.